Hello, my name is Chris West. I'm a passive house consultant. I have my own company, EcoHousesofVt, and today I'm going to be giving a presentation on Passive House and the Passive House building standard. First, history of the Passive House. The passive solar design and super insulation were actually originated in North America over 40 years ago during the 1970s. But after the crisis was over, the innovations that were discovered and created during that experiment were never actually taken into broader use. 15 years ago, a German scientist by the name of Wolfgang Feist created the Passive House Institute and designed the Passive House Energy Standard to define scientifically what a high-performance house is. And now the PH standard, Passive House, has been implemented throughout the world and has been acknowledged as a standard for sustainable architecture and low-energy house usage. The Passive House principle is based upon the highest energy standards applicable to all building types. So we're not just talking about residential buildings, we're also talking about commercial buildings. The main focus in the Passive House is a focus on energy conservation through making the building envelope as energy efficient as possible. That's where the name passive comes from, that you try to put a lot of energy and effort into making the envelope as good as possible so that the actual building during use uses as little energy as possible. It uses a very sophisticated energy modeling software to inform design decisions, and there are more than 30,000 of these structures built in Europe, so it's not as if Mr. Feist created the standard in 1995, built 3, and everything is based on 3 buildings. Now, there are more than 30,000 structures and buildings built in Europe, and these buildings are operating as designed. With a passive house, building the actual envelope is all in the details. We have an exceptionally high level of thermal insulation. We have a passive solar design to capture as many BTUs of heat from the sun as we can during the heating months. We use extremely well insulated windows with extremely well insulated frames and triple low E glazing. We build our buildings so that it is thermal bridge free, which means that there are no places, or as few places as possible, where cold can seep into the house or heat can seep out. And we demand a very high level of airtightness on our buildings. The current code, the RB's code, has an air changes per hour of approximately 4. The Energy Star has an air changes per hour of 3 at 50 pascals, which is about the same as a 22 mile per hour wind blowing on the outside of your house. The Passive House standard is 0.6, so less than 1 air change per hour. And we have a high efficiency heat recovery ventilation system. Because we build our houses very tight, we need to have this recovery ventilation system, but this also adds to the energy efficiency of the house. The results we get with the Passive House are a dramatic reduction in energy consumption. We're talking 90% less than a standard code house. Superior indoor quality. All of the monitoring that has been done shows that the indoor air quality of a passive house is almost as good as outdoor air quality. Occupant comfort. The Passive House is built and designed to function in such a way that all of the rooms are exactly the same temperature or near the same temperature, and that there are not huge temperature swings. Lower annual energy costs, which I just discussed, up to 90% lower. Smaller carbon footprint. The Passive House standard asks not only that we use a lot more less energy, and that we are able to use less energy because we're building with this standard, but also that when we're building the houses that we use materials that have a low embodied energy, as it's called, which means there's less energy required to actually make the materials that go into the construction. And it's a more durable construction because of the high quality or high level of quality that's required for building a passive house. In order to get that air tightness, we end up with a house that has less moisture infiltration, thus less mold, less damage, and thus a longer living and more durable house. The indirect benefits: one, it is the only energy standard that is able to achieve carbon neutrality, as heating consumption is up to 90% lower than a conventional building. And because the making of a passive house is actually done by local companies, we have seen a large increase in Germany of businesses that have been created to support the passive house industry. For instance, since Passive House started in 1995, there are now 50 new window manufacturers in Germany that build certified passive house windows. Those are jobs that we can also have here in America, and not only in America but specifically in Vermont, if we find industry leaders who are willing to take on creating passive house windows and other materials for passive house. Here's a chart that shows the difference between a code house and a passive house. Both houses approximately 2,000 square feet, and the millions of BTUs annually required to heat that house. A code house at 35 million BTUs, a passive house at 7 million BTUs, giving us a difference of 28 million BTUs per year. And here are different types of fuels that would be required to be used to heat that house at that BTU level, and what the difference is. The basic concept of the passive house is very simple. When we look at a thermal image of a insulated coffee holder and a Mr. Coffee, we can see that the coffee holder, where we put the coffee in, the thermos where we leave it hot for hours, when we take a thermal image of that, it's giving off very little heat. In the thermal image on the right here, you can see that as the temperature gets up, you can see that it gets closer to white. It starts at blue at very little energy loss, and all the way up to red, yellow, red, and purple, all the way up to white. And you can see that the Mr. Coffee, of course, is losing a lot of heat to the room around it, while the coffee thermos is not. Similarly, here we have a row of apartments in Germany, in Frankfurt. And before there was a passive house renovation on these buildings, the lower left shows the energy loss of those buildings. You can see a lot of white, certainly a lot of yellow, especially around the windows. But obviously we're losing a lot of heat through this facade in the house. Then when we go to the right, we see after the passive house renovation a thermal imaging of that same row of houses. And you can see there's almost no red. It's all green and mostly blue. And here in the middle we see the reduction of 87% in the energy use of that building to heat it in the heating season. Now we need to think about building houses and how we're building houses now in the context of our 21st century energy situation. The problem is, and most people don't know this, that buildings are the largest contributor to climate change. This is a chart which was put out by Architecture 2030, available through online at www.architecture2030.com. The source of this energy is the United States Department of Energy Information Administration. And as you can see, shockingly, beyond what we might imagine, that buildings and the energy that buildings use per year accounts for 46.9% of the energy that we use as a society. Transportation, where a lot of people are putting their time and effort in, and those are all very good initiatives, actually represents 33.5% of the energy used and CO2 emissions therefrom. And then when we break that down, energy used by sector, we see that not only are our buildings using more energy than transportation or industry, but that it's not building our houses and our commercial spaces that is the majority of that. That is that small yellow wedge, building construction and materials, but that 43.5% of all of the EU's energy consumed in the United States is for building operations. And building operations, a large part of that, of course, is heating and cooling. The U.S. energy consumption by sector, a historical chart, shows us, if we look at the top, we have the yellow, that's the buildings, that while industry and transportation are a large part of the energy that is used, the consumption thereof is actually leveling off over time, and that the increase in the energy used in transportation industry is not increasing at the same rate as the yellow, showing us that buildings and the projection of the increase in buildings over the next 20 to 30 years will be a more and larger portion of our energy use. This means that we need to look into making buildings that don't contribute to this change. And that seems like a large problem, but actually, with some care and a slightly larger price tag on a new house, we can reach that very easily. This is a historical overview moving from the 19th century. In the 19th century, the 1800s, we were building houses that had not very well insulated walls, not very well insulated ceiling or foundation, and we put in a rather large heating system of fireplace. But even with that fireplace in the middle of the winter, we weren't warm enough, so we also had to put on sweaters. So people were dressing for the outside, but living inside in their outside clothes, and using a lot of fuel to badly heat a badly insulated house. Then we got to the 20th century, where we got very good at designing mechanical systems that would heat our house. Oil heat with radiators, using steam in some places, even wood-burning stoves that are higher efficiency. And we loaded our house with these very low efficiency but very good heating systems. They used a lot of fuel, but they did the job. We could take our sweater off, but we had all of these systems throughout our house that required maintenance and replacement over time. And now moving towards the 21st century and how we can build buildings, how we can build our houses. Here we have the passive house concept. Here we have a house that's orientated towards the south so that we take advantage of solar internal heat gain. We have a very small air-to-air heat exchanger, pump in the wall on the upper right. And then we have that high efficiency heat exchanging ventilation system that recovers heat as it brings in fresh air. Architecture 2030 has a challenge, and the energy goal is to move towards carbon neutrality by the year 2030, thus the name of the challenge. And today we're at 60%. The idea is that we will move towards 70, 80, 90, and then 100% carbon neutrality. Other countries have been moving forward on this, most notably in Europe. Here's a chart showing the various countries within the EU and where their standard is now and what they're moving towards in the near future to get towards carbon neutrality, or at least in the direction of carbon neutrality. One example out of that chart is the Danish building code, where the gross energy, including heating, cooling, ventilation, and domestic hot water, was in the existing stock 145 kilowatt hours per square meter per year. And forgive me that we're using European numbers with this, with kilowatt hours and square meters, but that's how the information came to us. Then they set up an energy standard based on the existing buildings, and every number of years they cut down the acceptable new building code. So the BR 1982 is the building requirements from 1982, which were 15 to 20% less than the existing buildings had been. In 1995, that was again reduced by another 10%, and every couple of years they're reducing that more and more until by 2020 they'll be at the Passive House standard. Now, the energy standard that we believe is a good one to go forward with, it is certainly not the only one, but it is a very stringent one and will get us to our goal. It is supported by and developed by the Passive House Institute in Darmstadt, Germany, which is Dr. Feist's organization, and the Passive House Institute in the United States, which is located in Urbana, Illinois. Now, what is the Passive House Energy Standard? A lot of people know and have heard about LEED, or the National Green Building Standard, but both of those standards have almost nothing to do with energy use of a building. They're much more about using unused land that has been used for industrial uses in the past, brownfields as they call them, locating houses near public transportation so that people don't have to use their cars. Only 15% of LEED has anything to do with energy efficiency in the house. So you can have a LEED Platinum house that is not at all energy efficient. The Passive House Standard is really only interested in the energy use of the house and, as I said before, in the low embodied energy of the materials used. Here is the standard. If you can build a house that meets these 4 standard points, then you have a passive house. And those are a heating load in the house of 4.75 kilobTUs per square foot per year, a similar cooling load, so not more than 4.75 kilobTUs per square foot per year for cooling, which in our environment is much less of an issue. A total energy demand from the source. So what does that mean? That means the energy that has to be used at the power plant to make the energy that you get at your door of 38 kilobTUs per square foot per year. And as I stated before, an air tightness of 0.6 air changes per hour at 50 pascals. That's 0.6, so it's less than 1. Here's a comparison of energy standards that we now have. First, we have all the way on the right, we have the old buildings. That's like my old raised ranch on Hanley Lane in Jericho. And that old building, as you can see, has the red bar is the heating, the blue bar on top of that is the hot water, and the orange bar or yellow bar on top of that is household use. Then we have, next to that, going from right to left, the IECC 2009 code, which is the basis for the Vermont Energy Code. And that is a good bit better than what my 1975 raised ranch is doing energy-wise, but not a whole lot better. It's about a third better. And if you were to build a house to Vermont Energy Code at this point, that is the bar that you'd be looking at. One more to the left is the Energy Star, which is about 30% more efficient than the Vermont Energy Code. Building America, which is a program that the Department of Energy uses to try out new energy efficient measures that they will then roll over into Energy Star, is about 15% more efficient than Energy Star. And then at the left you have the Passive House. And as you can see, compared to the IECC 2009, which is the basis for the Vermont Energy Code, Passive House uses 1/10 of the energy. And most of that, if you notice, is coming from a reduction in the heating. So the red bar is the smallest of those. What are the economics of a passive house? I mentioned at the beginning that when you build a passive house, you're actually going to be spending a little more to build it in order to get very large savings later. This chart shows the development of a passive house by applying passive house concepts going down the line. So the leftmost bar shows a code house with a primary heating demand of 60 kilobTUs per square foot per year. And then we start with new massing and window location. So we make sure that we have our windows to the south and then we gain a certain amount of heat, which then comes off of what we have to add, so our heat demand goes down. We add windows, those high insulated windows with insulated window frames and triple glazing, and that brings another 15% off. We design it very carefully so that there are no thermal bridges. We then go to air tightness using a high efficiency energy recovering ventilation system, either an ERV or an HRV as it's called in industry. And then we get to the passive house insulation with in this situation, an air-to-air heat pump. And you can see that the red bar has gotten smaller and smaller all the way along, and that the blue bar, which is our primary energy demand without heat, which includes our hot water, our electricity for lighting, etc., that has not yet decreased. So we put in a solar hot water system that cuts that domestic hot water, and that leads us to our final passive house at 4.3 kilobTUs per square foot per year, which is then reduced further by other application of other design ideas. Now, when I said at the beginning that a passive house costs more, the actual data that's been coming in of passive houses that have been built here in Vermont shows that the passive house costs between 8 and 10% more than a standard house. Here we have an analysis that overblows that percentage. We have a $180,000 house, that's the cost of construction, the actual house, a code house. The upgrade here is estimated at 20%, which is about 10% more than what we're seeing in the field as to the actual cost of a passive house. So the passive house costs $216,000. In order to finance that, we need to take out more money. That's that $36,000. And that $36,000 is then something that we have to make back. That's then the payback moment. We're looking here at an estimated annual increase in energy costs, so the amount that energy costs more every season, which here is estimated 5%, but historically natural gas and propane in Vermont cost 7.5% more. And we've had some very large increases recently, although natural gas, if you're on the natural gas line, which most Vermonters are not, there has been a slight decrease due to fracking. And you can see here on the bottom chart with the bars that that's the point at which you get to zero on your payback. So that's the point at which the $36,000 in extra costs have been paid back due to the energy savings of the passive house. And that in this scenario is at about 7 or 8 years. Now we're going to look at a Vermont case study, and that case study is of an actual passive house that has been built here in Vermont. This is the Habitat for Humanity passive house. This is the floor plan for the passive house. This house has a 1,050 square foot usable floor area. The outside dimensions are 1,200 square feet. Here we have a downstairs with a bedroom, a bathroom, a living room, a dining room, and a kitchen. And on the right we have the upstairs with 2 more bedrooms and another bathroom. Here's what the house looks like. This is an important slide because it shows that unlike some building styles like the Earthship and other types of energy efficient building systems, this house does not have to look any different than a standard house in Vermont. All we have to do is make sure we hit that heat energy demand, the cooling demand, the air tightness, and the primary energy demand. So it can look like just about anything. Here we have a modified cape on the west and south elevations and the east and north elevations. You can see that we are having fewer windows on the north elevation. That's a part of that solar heat gain capture design. Now here's that same house after it's actually been built. This house is in Charlotte. You can actually drive by and see it. On this roof there you see our 2 domestic hot water solar hot water panels that's producing the majority of the hot water for the house for the year. And you can see the large amount of glazing on the south side of the house, but you can also see that it looks like just about any normal house. One more shot. This house does have excellent access to solar heat gains with a very open field to the south. This is a picture of the mechanicals for the house, and you can see the one thing that's missing from here is a heating plant. We don't have an oil furnace, we don't have a boiler. What we have here is the high efficiency heat gain ventilation that is right next to it with all of the aluminum tubing is actually a ground source heat loop. That's not a heat pump, but it's actually a heat loop, and that loop is used to pre-warm the freezing air before it goes into the ventilator so that the ventilator does not freeze up during very cold weather, and that's actually working very, very well. We also have to the left of that two tanks. The first tank going to the left, kind of a goldish colored tank, is the solar hot water collection tank. That is where the water comes from those panels that you saw on the roof into here and is stored and is then sent through to the actual hot water tank next to it. So if the water in the solar hot water collection tank is not hot enough, then it is heated that little bit that is the difference between what the solar panels can produce and what you want in your hot water coming out of your faucet, 120 to 130 to 40 degrees Fahrenheit, is bumped up by the hot water tank next to it. And on the ground over there is the filter for the well. Now there is actually a heating system in the house, but it is a 12,000 BTU air-to-air heat pump, which is basically about as much as 2 hair dryers. So we're able to heat this house with just a hair dryer. This graph shows something very important. There's often a question that we get about the comfort in the house. You can see the top of the graph shows the temperature. The right side shows the temperature, and then the bottom shows the dates. This is the entire month of December, which was admittedly a warm month for Vermont standards, but you can see what's really striking is the indoor temperatures. They're temperatures for various rooms which have been monitored. The orange circle is the living room where the heat pump is actually adding its heat. Then we have the upstairs bedroom, the downstairs bedroom, the upstairs bathroom, the downstairs bathroom, and upstairs bedroom number 2. And you can see that all of those numbers are very closely grouped. So while the orange circle in the first day, that 1 December 2011, was at 75 degrees, the coldest room, which is the room that's furthest away, was the upstairs bedroom and the downstairs bedroom, and they were at 72 degrees. And you can also see, as you follow it along, the red line here is the outdoor temperature of the air. That while the outdoor temperature of the air fluctuates up and down, that the actual indoor air temperature fluctuates very little and never gets below 68 degrees, which is the design temperature for this house. At the very bottom, you can see those blue bars. That's the heat pump usage in kilowatt hours, and that shows that over the entire month of December, the heat pump, which is the only source of heat beside internal heat gains like cooking and lights and the solar heat gains, was 135 kilowatt hours. At 18 cents per kilowatt hour, you can see that that's very little money. Another question we get about the passive house is whether or not we can maintain good indoor air quality. That's a very good question. Since we're making these houses very tight, we need to be able to show that we're able to maintain indoor air quality. The indoor air quality requirement from ASHRAE, which is the American Society for Indoor Air Quality for Ventilation, is 1,200 parts per million of CO2 equivalent. And you see on the right here that our graph starts at 535 parts per million CO2 equivalent and goes only to 585. That's because we only wanted to show in this graph the actual numbers that we were getting from the passive house. So the graph, if we were to show the indoor air quality requirements for ASHRAE, would be a much larger graph, and the data that we're showing here would be very small at the bottom, about half. Many indoor air quality experts agree that the indoor air quality of a standard built code house is much hovering around that 1,200 parts per million CO2 equivalent, and can actually go above that to where it's unhealthy and get back below that depending on the wind conditions and open doors and windows and that kind of thing. Here we have this high efficiency heat recovery ventilation system working 24 hours a day with very little energy use, and the indoor air quality is given here. The beginning of December, the indoor air quality was slightly worse at 580, but still half of the maximum CO2 equivalent for code. But for the most part, after that, you see that it levels off around 555 parts per million of CO2 equivalent. And that is just about 100 parts per million above outdoor air. So passive house, while it's very, very tight and all of the fresh air is being delivered by this high recovery ventilation system, we show here that the indoor air quality is very high. Next to that we see, or under that actually, we see these red bars. That's the HRV energy usage. That's the amount of energy that HRV is using, that high efficiency ventilation system. And here it is at kilowatts per day. On the average, it's using about 0.5 kilowatt hours per day. That's a half a kilowatt hour per day to ventilate the entire house for the whole day, 24/7. And a kilowatt hour costs 18 cents. So we're talking about the cost added to the house of ventilating with the system is negligible. This chart shows the energy usage of 5 Energy Star houses, and I showed you at the beginning that the Energy Star was about 30% better than code. So it's a relatively tight house, 3 air changes per hour. It has a 30% less energy usage, but still has quite a large heating plant inside of it. And so we have the first 5 are Energy Star houses, and then we have our passive house, which is low load number 1. And then we have a house that they've built that's close to passive house, which is low load number 2. You can see very clearly that the usage, these are actual usages that were compiled by Peter Schneider of the Vermont Energy Investment Corporation, which is the company that runs Efficiency Vermont, that the actual energy usage is 5 times, 6 times higher than the passive house. At 5,000, now there we get 10 times higher, 4,717, still almost 10 times higher than the 512 heat and domestic hot water load of the passive house. Now you may wonder why low load number 2 has 2,000 kilobTUs per square foot per year, and the reason is that house is actually being lived in by a family from the Sudan, and that family likes to keep their energy, the heat in the house at 90 degrees so that they're more comfortable because the winters here are quite cold. So that is because instead of keeping the house at 68 degrees, that family has opted to actually increase the heat in the house. But still, even with that 90 degree temperature in that house all year, we're still seeing a usage that is a third of some of these Energy Star houses. This is the chart that says it all. This is the average use of this house from June through February. This is the actual usage of that house on electricity. And here it's important to note that this is the entire electric bill that this house had. And this house is heating with electric, its hot water is electric, its cooking is electric, and its lights, computers, game consoles, televisions, and other types of electronic devices. All of that is in this number. And you can see that the number does go up in January to $132 for heating, hot water, cooking, game consoles, computers, televisions, and everything. But the average monthly cost is $67. And when we look at how much of that is actually created by the heating demand, it's estimated by Peter Schneider of VEIC that $20 average per month is being used to heat this house. So these people are heating their house with $20 a month average, $240 a year to heat this 1,000 square foot house. That is the future. Now I'm going to just show you some houses here to give you an idea of what Passive House looks like in Vermont, and also to let you know and see that passive houses can be of various designs. Here we have 3 houses. The center house is the passive house. They all look very close together, but that's really just the angle. The 3 houses have quite a lot of distance, more than 100 feet between them, so that the house on the left here is actually just set back further from the road, and the angle that they're shooting at makes it look like they're close, but they're not actually that close. So that center one is the passive house. The one on the left is slightly less than a passive house, and the one to the north is slightly less than that, because they wanted to see about the energy usage of various levels of insulation. So they brought the insulation on the house to the left and the house to the right down a little, but they're very similar in design, and all 3 of them could be passive houses. Here we have the Middlebury College Self-Reliance House. There are 3 students living in this right now. This is a passive house. You can see the solar domestic hot water and the PVs on the roof, and there are some students in it right now. This is a house, 2,500 square foot house, I believe it is, in Stowe, Vermont. So the size of the house can also be passive. You can make a big house passive, you can make a small house passive. The average house size, actually, since the crisis began, housing crisis began in 2008, has gone down by a number of 100 square feet and is now around 2,000 square feet nationally. But this is quite a large house, but also a passive house. This is a passive house that's built in Norwich. Once again, you can see that the shape of the house can be just about anything. You do notice that there are not many dormer windows and not many bump outs, and that's an important part of keeping the thermal bridging down on a passive house. Those things can be built onto a house, but we prefer not to do it because the added cost to insulate that to get the thermal bridges dealt with. Here is a salt box that's now being built in Brattleboro. This one is not built on a slab, it's built on piers, and so they've super insulated the floors. Those are the Thermatech windows that you saw modeled in one of the charts above, and this house is also a passive house. This is a house that is now being built, in the process of being built in Charlotte, and is also a passive house. This is a house, this is only the entry level, that's being built in Moortown. This is being built as a part of a modular house, the modular part being built by Preferred Building Systems in New Hampshire, who also built the units for the passive house in Charlotte. And here's another. So once again, lots of different options. Can be more modern, can be less modern. Here's a number of apartments that they're building, passive house apartments in Hartford. And this is a slide that shows that this presentation was put together by Enrique Bueno, Peter Schneider, and myself. And I'd like to thank you for taking the time to look at this particular presentation on Passive House. If you have any questions about this presentation, please be free to contact me. My website is EcoHousesofVt.com. info@ecohousesofvermont.com, and I'm available for giving this presentation publicly. Thank you very much.